2, 1.
All right, cool. So thank you all for coming. Today, Baki will be telling us something. So whenever you're ready, begin to say.
Very nice. All right, thank you very much. So the math subject of the talk today is going to be a proof of Liouville's theorem using some very over-the-top stochastic analysis methods. But it is Dr. Seuss's birthday today. And for those of you who don't know, Dr. Seuss, his real name is Theodore Seuss Geisel, as in the Geisel Library at UCSD. So there are many connections between the Geisel family and UCSD. In particular, I think in the 90s, there was his wife made a donation of a large amount of his work to UCSD. And then actually in the year of my birth, I believe is when she donated the huge thing, the $20 million or something for the library. And so
you should get born more often, Baki.
I should, yeah. It's good stuff for UCSD. So I thought I would do a little bit of a tribute to Dr. Seuss. So that's the little introduction there. And now I'll get my screen shared. Okay. Get myself set up. Okay. Let F be entire, if you so desire. Well, even if not, 'tis what I'll require. Suppose, in addition, despite its ambition, that modulus F obeys the condition that no matter what, it cannot go higher than some constant C, which F quite admires. My mission today is 1, to inform, and, in honor of Seuss, 2, to perform a dramatic rendition of a proof of the fact that any such F is a constant. How whack. The proof I'll present is kind of insane. We'll use some deep theorems. It's far from inane. I'll leave out the details because they're a pain, but if you are curious, then don't you complain. When it's all said and done, I'll back up to explain a bit of analysis to keep myself sane. And now it is time. Without further ado, what you say, Sam?
Go ahead.
Thank you. Our story begins with Brownian motion. Wait, huh? What's all this commotion? Weren't we discussing some entire functions? You must have had a severe malfunction. I know. All in due time. Hold on a bit. Don't throw a fit. As I was saying, Brownian motion. It's notoriously not the simplest notion. Supposedly, it models random motion of dust. But that's not quite so helpful. A concrete description's a must. Consider a sequence of Bernoulli 1/2s, all independent. Sum them up, draw some lines. Well, here are some graphs. By a theorem of Donsker, this sequence converges, and from this result, our definition emerges. Now, the real line's nice, but not quite enough. Without complex numbers, my proof's just a bluff. Brownian motion on C is what you'd expect, except maybe this root 2, which I often neglect. Though there's many a fact I could share with you now about Brownian motion, I'll hold back, I vow. I'll try to streamline this freaking development, proving Liouville. On that I am hellbent. We're almost equipped for the proof's crucial step. There's just one black box I'll need you to accept. We'll discuss it more after the proof is complete. I beg you for now, allow me to cheat. Let G be a function that is real C2. Then, with this notation I have written for you, we have the following stochastic chain rule. It's a complexified version of Ito's formula. If G equals F, then D bar is 0, and D equals prime, which will be our hero. I'll pause here a sec so you can reflect, because there's another equation to check. We're almost there. Just one more tool. It's a stochastic version of the product rule. Well, here you go. I'll pause for reflection. It's the usual product rule with this correction, where dbt bar equals dt, and the rest disappear, which makes it easy. Let's now apply this to modulus f to the power of 2, which is f bar times f. Using the formula we had before, with the rules above, we get this eyesore. But a magic thing happens when we take expectations. Fact, these terms disappear, which is cause for elation. Here's the final result of this strange calculation. I'll use it to finish the present oration. At last, we invoke that f is bounded. What we shall find will leave you astounded. It follows indeed that this integral's finite. This means that f, as I'll show you if you sit tight, try all that it might, must be a constant. So much for the hype. Indeed, if f is not constant, then f prime's not 0. So choose a point z at which it's not 0. Let epsilon be this non-zero number. We're almost there. Fall not to a slumber. Since f is entire, f prime is continuous. So there's a disk around z on which f prime's conspicuous. If we call this disk D, then we can and do see, bada boom, bada bing, infinity. Our goal is achieved, our mission accomplished. I hope that the proof was as cuckoo as promised. Though rhyming is great, for now I am done. Thank you for listening. I had tons of fun. All right, so that was the Dr. Seuss tribute portion of the talk. And now I'm going to discuss a few of these many horrendous details. So the first one, I will completely ignore the stochastic calculus. And let's just assume that what we get is if f is entire and bounded, then this formula holds. Okay, so this is essentially like you can pretend that we know what Brownian motion is, and Brownian motion is essentially the most natural way that you can pick a random curve, a random continuous curve, and it's more or less the closest you can actually get to having a random path that at each time is normally distributed with mean 0 and variance t, and each path, each time bs is independent from bt. So it turns out that if you have a random path, so that let's call it p, a random path p, so that ps is independent from pt, it's not possible for p to be continuous. So it's actually impossible to do the thing I said literally, but Brownian motion is the closest you can get to such a thing. So let's assume we actually understand what's going on. And I said it's a random path, so we can take expectations. There's an underlying probability space. And now what I'm telling you is ignore how we got this formula for the moment. And let's just say that we have the formula. If f is entire and bounded, then the expectation of the modulus squared of f of the Brownian motion is the initial point plus the integral from 0 to t of the expectation of the modulus squared of f prime of the Brownian motion.
And just to clarify,
yes.
This f of bt is you take a Brownian walk for t time, and then you take that point and plug it in that.
Yes, and so I should also thank you for the question. So I should also recall that my B was a Brownian motion in C. So this is you should really view it as planar Brownian motion, meaning like a random wiggly in the plane. And yes, so we just plug in that random path into the function f. Similarly for the function f prime. Okay, so I obscured it in the talk, but actually getting this formula in a fully legitimate way requires a certain condition on f that boundedness is enough to assume. So actually, even this formula, we kind of used f as bounded, but I'll ignore that. So let's assume that we have this formula. And now, like I told you before, if you look at this term and move this one over, what this says is that if f is bounded above by c, what this says is that for all t greater than 0, this integral that we'll be interested in a second is bounded above by c squared minus modulus of f of 0 squared. So in particular, if we take t to infinity, this is a non-negative function. So basically any manipulations that I do are allowed by very standard measure theory, or in this case, actually even Riemann integration theory. What I conclude is one of the pieces that I had mentioned, that if I integrate from 0 to infinity, this is finite because it's bounded above by this constant. Okay, so now the important claim at the end of the proof was that if f is entire and bounded, oh sorry, if f is entire and non-constant, let's say, then this cannot be finite. So now this actually is where we use in a very strong way the fact that we are using Brownian motion in dimension 2. And I will show you very explicitly what happens here. One important thing I should mention is that this is actually a simplification of a lot of arguments I've seen that that do this method, and usually people use something like they use what's called a strong Markov property, and they have a step that's really kind of iffy on the details, but I think this is kind of a simplification of the standard argument. So if you kind of look this up later, you won't find exactly this, you'll find similar things. Okay, so let's go through that last bit of the proof where I show that if f is non-constant, then this has to be identically infinity, because there was an important calculation that I omitted there. And actually, it's sitting above. I'll go back to the last part. So if we assume that f is not constant, that's exactly the same as saying the derivative is not identically equal to 0. And so we're going to choose this point where f prime is not 0. And we're going to use the continuity of f prime to say that there's a disk around the point z, so that on that disk, f prime is at least 1/2 of this point that I took in modulus. And that's like a simple application of continuity. Okay, so here's now our new datum, that on the set D, on the disk D, which recall is a non-empty disk, so it has positive area, that'll be important for us, f prime is at least epsilon. So now I'm going to go over these details, and then maybe not quite these details. I'll BS about these details. So let's check out this calculation. Our goal is to show that this is infinity. So here's the calculation that in the end accomplishes that. Okay, so this is non-negative. So if I make it 0 sometimes, this will always be bigger, okay? So this is bigger than if I tell it to be 0 when B is not in the disk. So that's what this step is here. And this is the admittedly terrible notation for indicator functions. And what this means is that this is the function that is 1 if BS happens to be in D, and it's 0 if BS is not in D. Okay, so now I'm going to use that fact that on the disk D, f prime is greater than epsilon in modulus. And now if BS on this set, if BS is in D, then we are plugging something into f prime from D. Okay, so that means that this right here is bigger than or equal to epsilon squared because of the square times the what's left over. Okay, and now the expectation of an indicator function is the probability of that set. So this is the probability that BS lands in D. And actually, BS is a normal random vector. In R2. And there is an explicit formula for the density of such a dude. And modulo constants that I may have screwed up. The formula, the explicit formula for this is this right here. And by the way, I have replaced my dummy variable for some reason, but this was an S before, and it's a T now. And this Brownian motion has variance T, and that's where these T's are showing up. Okay, so the last detail is essentially the claim that this double integral is infinity. It does not converge. So as I was saying, there's a basic fact in measure theory that if you have a non-negative function, then you can always flip integrals, any integrals you want. That's called Tonelli's theorem. People often know the Fubini's theorem, which is in some sense less restrictive, in some sense more restrictive. So Fubini's theorem tells you when you can flip integrals for functions that may or may not be non-negative, but for non-negative functions, even if you have integral equal to infinity, you can flip any integral you want. So
there's also the undergrad version of Fubini-Tonelli, which says you can always flip integrals.
Yes. Okay.
No restrictions.
That's very good. By the by the calculus version,
the freshman's dream of
yeah. So we're gonna always flip integrals because they're always flippable. Very good. Okay. So now x and y, once I flip this integral, are now fixed. So I'm just like this, for all intents and purposes, is just a constant r. Okay. So now the claim is that actually this inside integral is always infinity. And roughly speaking, it's because we're dividing by t. And this guy, if you go far out in time, it's basically equal to 1. So we go far out in time where it's at least 1/2 or something. I don't care about the small t's, but for big t's, this is going to be at least 1/2. And then this will be 1 over t. And that's not integrable. So actually, it's always just infinity, this inside integral. And now the key thing here was that, the area of this disk was not 0. So if this area of this disk was 0, then I could be tricking you and saying this inside integral is 0, but it's really 0 times infinity. Or sorry, this inside integral is infinity, but I could have been tricking you and saying 0 times infinity. And actually the convention in integration theory is that 0 times infinity is 0. So that would have been 0. But this disk has positive area because it's like a non-empty disk. And so actually infinity times area of the disk is infinity. So at the end of the day, if f is not constant, then f prime is not 0. And if f prime is not 0, then actually this integral is infinity. And I'm going to point out, go ahead, Jason.
Oh, is there some way of viewing that integral being infinity, like equivalent to saying you visit the disk infinitely often?
So I think it's maybe a couple steps away from being a fully rigorous proof of that statement. But what I am essentially doing, so there's this fact that if you have Brownian motion in RD, when d equals 1, Brownian motion is point recurrent, meaning it visits every point infinitely often, almost surely. So that's what point recurrent means. In dimension 2, Brownian motion is neighborhood recurrent, but not point recurrent. So meaning it doesn't visit every point, but actually every non-empty open set, it visits infinitely often, almost surely. And we are essentially applying not nearly the full strength of that, but basically some of the strength of that to say that that integral is infinity. So that's more or less part of the proof of this neighborhood recurrence. Also, I should mention that if we, for some reason, encountered this this calculation and we were in dimension 3, instead of 1 over t here, it would be 1 over t to the 3/2. And that is integrable for large t. And so that's actually the reason. This is kind of where this being a t to the 1 instead of a t to some other number, that's where we use that we're in dimension 2. We're in the plane, in the complex plane. And so that's part of the reason that this works. And as Jason pointed out, this is more or less saying that Brownian motion visits the neighborhood a lot. Okay. All right, neat. I'm very glad you mentioned that, because there are a couple other proofs that are basically this, but they either use the full strength of recurrence, which is not quite necessary, or they leave unattended a very important stochastic analysis detail. I won't talk about that at all, but there are some very incorrect proofs out there that neglect some of this. Okay, so that is why if we have this identity in the first place, then we can finish the proof of Liouville's theorem. And actually, I'll mention that, well, okay, maybe we'll talk about stochastic calculus a bit first, and then I'll make an additional remark. So are there any questions up until now? Sweet. Okay, so now let's talk a little bit about stochastic calculus. So if you're in a particularly like gung-ho basic real analysis class in your undergrad years, you would certainly, even a more basic one, you would certainly define, I should stop using t's, or I'm going to mess it up. So you would certainly define integral from a to b f of x dx, where this is a Riemann integral. And it would be a limit of Riemann sums where you were allowed to choose in your evaluation point. So let me see if I can BS some notation about this. F of
I thought we were done with the BS notation.
Oh, very good. T j plus 1 minus tj. Oh, I'll do delta j/t. Okay, cool. So this is some partition of a to b, and you're allowed to choose any evaluation points you want. And as the mesh of the partition goes to 0, those Riemann sums converge no matter what evaluation scheme you chose, and they converge to the same number. If, well, that's the definition of Riemann integrability. But if, for instance, f is continuous, then such a procedure works. So you may, yes, so if you're in a gung-ho real analysis class, you may also define this integral, which is called a Riemann-Stieltjes integral, where the goal is, again, to get Riemann sums. So where this increment is using the function g instead of the function the identity. Now, these Riemann sums don't always converge in the same circumstances they do for Riemann integrals. In particular, you want to be careful about what kinds of g's you use for this. Does anyone know or remember what kinds of g's you often restrict to when you do Riemann-Stieltjes integration?
They're often differentiable.
They are often, yeah. So the easiest condition is you can do continuously differentiable. And then actually, in the end, this will be g prime of x dx. this will be the integral of f of x times g prime of x dx. The more general condition, which is maybe the standard one if you want to push Riemann-Stieltjes integration to somewhat of an extreme, is bounded variation. So that, I'll use my notation from above. So that means that if you take the supremum over, let's say, all partitions of A and B of G of T J, okay, so I've changed my Tj minus 1. So if you take the supremum over all partitions, T0 through Tn of the closed interval AB, and you do this increment with the absolute values in it, this should be less than infinity. So in particular, actually, if G is increasing, then you could take these absolute values away and telescope the sum, and you just get G of B minus G of A. So actually, increasing functions allow you to do Riemann-Stieltjes integrals, but not general functions. And for us, we're going to kind of want to put Brownian motion for G. And there is an unfortunate fact. So this is called bounded variation. So again, we're going to pretend that we really understand Brownian motion. And you can prove a theorem that actually almost surely, so basically all the time, Brownian motion, so the taking this to be G, is of unbounded variation. Variation on all closed intervals that are more than 1 point large. Shut up, Sam. More than 1 point large. You need at least 2 points in the interval. Okay. So basically what this means, and you can also prove some no-go theorems about Riemann-Stieltjes integrals in circumstances like this. So more or less, this says that if you want a general Riemann-Stieltjes approach, you're doomed if you're going to do Brownian motion. If you want to, can't do Riemann-Stieltjes integral f dB as above. So this is essentially the issue that stochastic integration theory was invented to solve. And the complete BS way that I will tell you the result of this theory is that in many, many circumstances, you can, this is the standard notation people use, you can integrate many, many types of processes. For instance, if you know a little bit of stochastic terminology, you could take X to be continuous and adapted, whatever that means, but basically continuous. And you can define this integral as a certain kind of limit Let me move over a little bit. No, I can't yet. Okay. Of x tj minus 1. So I'll comment on that in a second. B tj minus b tj minus 1. So the tj is a partition t0 through tn of the interval 0 to t. And really, I guess I should put n's in this notation because the partition itself depends on n. And I'm taking a sequence of partitions with mesh going to 0 as n goes to infinity. So this is the same sort of situation that you are in when you do Riemann integration. But the key difference, this looks basically the same as what I wrote above. The key difference is that you always take the left endpoint of the partition. You're not allowed to choose other partition points. You can actually show with some examples that you get different answers. Sometimes they still converge, but you get different answers if you use other evaluation schemes. And so actually, this choice of the left endpoint is what gives you Ito integration theory. You can build theories with a number of evaluation schemes like right endpoint evaluation or midpoint evaluation. The midpoint evaluation is called Stratonovich integration, and that one is useful geometrically, and Ito integration is useful probabilistically. I'll leave it at that, but I just wanted to mention that you can do other evaluation schemes and get other integration theories.
I'll also know that the midpoint evaluation has a lot of regrade requests.
Amazing. Okay, so now I have hand waved about what integral against Brownian motion means, even though I have not told you what kind of limit this is. Whatever. Okay, so the next thing I want to tell you about is we saw terms like DMT and DNT, and that looks whack. So at this point, I would say it's acceptable for me to write the differential notation of this as xt dbt, and we understand that that's the differential notation of the integral of x db. Fine, but what the hell is this DMT DNT? So actually, this is, yeah, let's see. So the way you should interpret this is that this is another device that you can use to integrate other processes. So again, keep x, say, continuous. This is defined to be, and theorem, this makes sense. We do the same scheme here with the integrand, but now we have a what's called a second order Riemann-Stieltjes sum, where we literally, just like you do for intuition for Riemann-Stieltjes integrals, you replace the d's with deltas, and you just do that. So you put the increment for, that shouldn't be a -1. You put the increment for m, and you put the increment for n. So this second order Riemann-Stieltjes sum converges, and it's how we interpret expressions like this as limits of these second order Riemann-Stieltjes sums. Okay, so now I have done enough hand waving to make sense of an equality like this. As long as m and n are such that this converges appropriately. And what this is, the definition of what this means is that y is equal to its value at 0 plus the stochastic integral x db plus this second order Riemann-Stieltjes integral z dms dns. So that's the definition, if you will, of such a stochastic differential equality. So that's what I mean when I write stuff like that. Now, if we forget the stochastic setting, what I've basically redefined for you is a way to write down the differential equation dy dt equals, I don't know, a of t times z of t. So rewriting that, I could write dy of t equals at zt dt. And actually, I could have just written, we're not doing differential equations yet, so I could have just written that. So in the non-stochastic setting, when I'm not integrating against crazy stuff, I've basically made this definition for you. And in this regular old setting, there is a chain rule that we're familiar with. So let's say you have some differentiable functions of one variable, f and g. Then the composition is differentiable, and the derivative is given by f prime of g of t, g prime of t. So I'm going to rewrite that a little bit using this BS differential notation. Okay, so I've just made this prime a d dt, and I've thrown the dt on the other side. Well, this is dg dt, so I will cancel those dt's. And I have this more stochastic-y looking differential equality. And actually, per the remark that Sam made at the beginning, if we interpret this as Riemann-Stieltjes integration against G, if G is C1, then this actually is, this adheres to the notation we said before. So let's say G of 0 plus integral 0 to t of f prime g of t dg of t, where I am Riemann-Stieltjes integrating against the function g. So fact, this is a fact, if g is c1, so before you only have to assume differentiable, but you should assume c1 here, and f is, okay, you can put more technical conditions, but I'll say f is c1. So that's the integral version of the usual chain rule. Basically what I'll end this on, and then we will go look back at one of the formulas I showed you. I'll end this with a statement of a very basic form of Ito's formula, which is the stochastic version of the chain rule. So if you note what happened here is I have, a process G and then a function that I apply to the process. And I want to know what D of that function of the process is. And in the classical world, I get D of, as I've written just now, f prime of g of t, dg of t. Okay. So there's a general formula for Ito's formula, or there's a general form of Ito's formula. I'm going to write it with very few assumptions, but then I'll show you what it actually means in Brownian motion case, and that'll be a little more connected to what we just talked about. So one version of Ito's formula, which is once again the stochastic chain rule, is that if x is an appropriate stochastic process, whatever that means, and f is a C2 function in which we can plug x, then the composition f, where you put in x, satisfies so this term is the term you would expect, f prime of g of t, dg of t. This is f prime xt, dxt. And now this is the term that's called the Ito correction term that you may not expect. F double prime xt dxt dxt, where again, as I defined above, this is like defined as an integral against a second order Riemann-Stieltjes increment. So that's Ito's formula, which is a stochastic chain rule. And actually, this simplifies in the case of Brownian motion. dBt is dt, and that's kind of one of the relations we used. And so if x is just bt, This is Ito's formula for Brownian motion, and in one variable. There's a higher dimensional version where you use the matrix of partial derivatives, and this becomes the Laplacian of f instead of the second derivative for higher order Brownian motions. And that's why I was mentioning harmonic functions earlier. The Laplacian, harmonic functions are such that the Laplacian is 0. And so actually, one very important thing we kind of used in the proof is a disappearing of some terms due to the harmonicity of analytic functions, let's say. So the last thing I'll do is I'll just go back with that, a little bit of context for what a stochastic integral is and what Ito's formula is. So from the two-dimensional Ito formula, there we go. From the two-dimensional Ito formula, I told you you're supposed to put in some partial derivatives and some Laplacians and do a little bit of messing around, but I will not derive it. But this complex Ito formula is a complex chain rule type deal in the stochastic world, where one uses the rules for two-dimensional Brownian motion from the standard Ito formula and reorganizes it with some i's in appropriate places. I can actually go into more of that with any of you later if you would like, for instance, in the Gather Town after. But for now, that is all I had to say to you. And thank you guys for listening.
All right, let's thank Baki. Yeah.
Thank you.